there is not much new that I'm going to do in exponential functions because we've already done exponents. So all the same laws of exponents work, but we are going to go back and review a few things. So the first thing I'm going to say is function notation, which we didn't really talk about in the course so far. So function notation, I've been writing equations like this, for example. So y equals. Now function notation is just another way to write y, which is to say that y is the same as saying f of x. So this is, you read this as f of x. So f of x, which is y. It's just another way to write y. And the reason we have another notation is it's useful for things like word problems. Say if we were talking about the cost of a product, then we might say C of x. So we could say C of x is the cost of producing X number of items. And so it gives a little bit more information than just saying y equals. Okay, so and what happens is if you go on in math, there's more than just, say, x in an equation. We might put t for time instead. There might be a time and a number of units, like both an x and a t in an equation, which doesn't happen in first-year calculus, but if you go on, it will. And then you need to use function notation, because if there's more than one letter in the equation, you need to know which one you care about. So sometimes one is a constant. So if there was an equation 2xy plus 3x squared minus 2y, and we only cared about the x, then the y would be considered a constant, and you'd treat it just like it was a constant. But if you cared about the y, then you could say f of y. So, and you would definitely not want to say y equals, because then it would be really confusing. So using function notation, it is nothing new. It's just saying that y is equal to f of x means the same thing. So it's just a different way to write it. So we're going to go back up to this equation that I've written. So f of, let's call it f of x is equal to 2 to the power x plus 3. So if we were to do a table of values, for example, so a table of values, say I want to plug in the values 0, 1, 2, -1, -2. Okay? So, and I put y here, but you could write f of x. They mean the same thing, so it doesn't actually matter which one you put. Now, what do we do to fill out the table values? We just plug those numbers in and work it out. And these are exponents, so we're just going to practice this. So if we plug 0 in, so what you could say is f of 0 is equal to 2 to the 0 plus 3. Now, what's anything to the 0 power? Not 0, 1. 1 plus 3, so the answer here is 4. What about f of 1? So f of 1, 2 to the power 1 plus 3, 2 to the power 1, 2 is 5. 2 to the power 2 plus 3, 2 squared is 4, is 7. So 5, 7. Now what about negatives? 2 to the power -1. This is really what I wanted to show you, but we started with ones that were easy. What does 2 to the -1 mean? 1 over 2 to the 1. A negative exponent means a fraction. So this is the same as saying 1 over 2 to the power 1 plus 3, which is 1/2 plus 3. How do we figure that out? Common denominator. So this is like a 3 over 1. So 1 over 2, multiply that one by 2. 6 over 2. So 7 over 2. And then the last one, 2 2 to the negative 2 plus 3. So what's 2 to the negative 2? 1 over 2 to the power 2. You change the exponent to a positive 2, so 2 squared. So this would be 1 over 4 plus 3. Multiply that by 4 to get a common denominator, 12 over 4, so 13 over 4. Okay, so and then if we wanted to graph this, we're not going to use this as a basic graph, although I will show you the shape right now. You could plot these points and you would get the basic graph. Now, let's draw that. So we're just going to plot these as points. So 0, 4, 1, 5, 2, 7. Negative 1, and 7 over 2 is what? 3.5. So here. And 13 over 4. Well, 12 over 4 is 3, so it would be a little bit more. So, say like that. Minus 2 and 13 over. So if you drew some tick marks, it would be better. There, move the points so they fit. It looks kind of like a hyperbola. Okay, so the difference is this. Like, is that shape, sort of that skateboard ramp shape? It is similar on one end only. So what happens is that, so the function is here. There's a 3 at the end. It doesn't pass 3. It doesn't go below 3. So here's y equals 3, but this one, it doesn't have an asymptote on the other side. This just keeps going bigger and bigger and bigger and bigger. You hear in the news like exponential function or an exponential growth. It means it's growing really fast, and that's what this does. So the basic graph is sort of like a hyperbola, and this end is like the skateboard ramp. It never quite touches that line, but the other one doesn't have a restriction. It just goes up and up and up. Now, we're not going to do more graphing than that. That's really it, okay? But I wanted to show you what the graph looks like. You can always do a table of values if you need the graph. And there are some things that are always the same on the different graphs. And we'll see that later, but we're not going to spend a lot of time graphing those. Okay, so the other thing we need to know about exponentials is that there is what we call a natural exponential function. So f of x is equal to a to the x. So any exponential function is of this form. A is a number. It's not 0 and it's not 1, but it can be any other real number. So let's say a is greater than 0 and not equal to 1. That doesn't mean it's greater than 1, because it could be a half or 0.2 or 0.3. It can be a decimal. It just can't be negative, and it can't be 1 itself. Okay, so for example, we can have 2 to the x. 2 is called the base. And x is the argument, or the variable, in this case. And then what we have is an e. Does anyone know what e stands for? It's like pi. Pi is an irrational number. Pi is 3.14. What's e? Does anyone know? 2.71, yeah. It's close to 2.71. It just occurs in nature. It's called the natural exponential function. And it occurs a lot in sort of engineering applications. If you were to look at a power line, so think of a power line with the 2 end posts, and then, or a clothesline, something like that. The curve, that shape, that basic shape is the same on every power line. It's attached the same height on either end, and it has a nice curve. That curve has exponential e's involved in it. Okay, so I'm not going to write the equation for it. It's more complicated than just E, but it has that shape in it. The other place where you see that is a bell curve. You've heard of that when you're some people ask if you grade on a curve or something like that. So, but you see this in statistics. That also is an equation that involves E. Okay, this is actually e to the minus x squared. So this one's more complicated. E to the x plus e to the minus x over something else. I don't know it right off. But those involve E. Okay, so that's just where it comes from, but it is just a number. All the graphs of exponentials go through the same point right here. So say this is a graph of e to the x, okay, 2.7 to the power x. 10 to the x would be steeper. 10 is bigger than 2.7. And on the other end, say 2 to the x, well, that's smaller than e, so that would be lower. So the higher the base, the steeper the graph, okay? So the higher the base, and actually the opposite on this side. The bottom one here is 10 to the x. And that's when the exponents are negative. So the bigger fraction, a bigger bottom on a fraction means a smaller number, so the 10 will be a fraction with a smaller bottom. But the graphs all go through that point. How come? Say we have f of x is 10 to the x. If we put 0 in, what do we get? 10 to the 0? 1. So that's the point 0, 1. If I said my graph was 2 to the x, and I put 0 in, also 1. It doesn't matter what exponential function I put in, 100 to the power x. 100 to the power 0, which is 1. They all go through that same point. So that's sort of your start point if you were graphing them. But again, you just do a table of values and you'll get the right spot for them. And I'm not going to ask you to do that, but I just want you to know what they look like because you will need them in calculus. Okay, so you can go back and look at them and see how that works. Okay, so let's solve some equations. So first thing, I want to say an example. Given f of x equals minus 4 to the 2x plus 3, find f of 0, f of 1, f of 1/2, f of negative 1/2, and f of 1/4. So basically a table of values that I'm not writing it as a table. We're just going to evaluate each one separate. So f of 0. So all we're doing is saying, okay, well inside this bracket is telling what we want the x value to be. So we want x to be 0 here. So we'll plug it in. Negative 4 to the 2 times 0 plus 3. Now, I did this on purpose because a lot of you get it wrong when there's a negative. This is negative 4 to the 0. And what's 4 to the 0? 1. This is negative 1 plus 3. How come it's not positive? How come it's still negative? The negative is in front of the 4. The negative is not to the power. It's not this. That's a different exponential function. Do you see? We're not saying negative 4 to the power 2x, we're saying 4 to the power 2x with a negative in front. Another way you could see this particular function would be 3 minus 4 to the 2x, and you probably wouldn't get it wrong if I did it that way. You would say 3 minus 1, which is 2. Okay, what about the next one? F of 1. So minus 4 to the 2 times 1 plus 3. So minus 4 squared. 4 squared. 16. Minus 16 plus 3. So the minus is in the front. Now what about putting a fraction in? So minus 4, 2 times 1/2. What's 2 times 1/2? 1. 2 times 1/2 is 2 over 2, which is 1. So what's the answer to this? Minus 4 plus 3 is negative 1. Now what about negative 1/2? Minus 4 to the 2 times negative 1/2 plus 3. Minus 4, 2 times negative 1/2? Negative 1. Still 2 over 2, but it's negative 1 plus 3. So now what's 4 to the negative 1? A fraction, right, 1 over 4. So this is negative 1 over 4 plus 3. (11 over 4). It's like a 3 over 1. You need a common denominator. Now the last one is 1/4. Plug it in. Minus 4 to the 2 times 1/4. 2 times 1 over 4 is 2 over 4, which is 1/2. Right? So we've got what? Minus 4 to the 1/2. What does the 1/2 power mean? Radical. It's a square root. So this is the square root of 4. And it's okay because the negative is in front. This is, the 4 is to the 1/2. Square root of 4 is 2. So that equals 1. Okay, so watch, a negative in front of something is not attached unless it's in the bracket. Okay, unless there's a bracket in front. Keep putting it in front. If you need to, write it as minus 1 times 4, and then maybe you'll not, then you'll put the minus 1. This is minus 1 times 4 to the 1/2. That's what the minus in front of something means. Okay, it's not attached, it doesn't go with the exponent unless there was a bracket around it. Okay, so that's sort of the hardest example, and there's some of those on the homework practice. But what if I put e to the x, and I wanted you to find e to the 0, or f of 0, f of 1, f of minus 3, for example. Now we have no calculator, we're not going to put it as a decimal, we just leave it. So the first one, f of 0, is e to the 0, which is 1. So that's okay. F of 1 is e to the 1, and we just leave it like that, e. Okay, nothing to do. And what about f of negative 3? 1 over e cubed, and that would be the answer. And you just leave it like that. Okay, so if it has an e in the question, you leave it. There's a case when we don't, when we can evaluate it, but that's in the next section. Okay, but basically that's the idea. If you get an e squared, e to any power, make the power positive, and that's the answer, and you stop. Okay, so the last thing in this section is solving exponential functions that work nicely. The ones that don't work nice are in the next section. So these we are going to solving exponential equations, and we're going to call this one type 1. Type 2 and type 3 are in the next section because they involve logs. So these ones don't. These are the ones that work nice and you don't need a log to solve it. Okay? So the procedure is this. Is to rewrite both sides of the equal sign. We're going to write the steps and then I'll show you what it looks like. To have a common base. Then compare the exponents to get the answer. Okay, so just looking at sort of step 2, if we have an equation, so there's an equal sign in between, we're asked to solve for x. What's x? Look at this. You shouldn't have to think too hard. I could give it to my son and ask him what x is. And with a little prompting and maybe changing the x to a circle or a box for him to fill in, he could tell me what to fill in there to make these two sides equal. What would it be? 3. X has to be 3 for the two sides to be equal. Do you agree with that? Yeah. So the answer to this equation is just x equals 3. So don't get thinking too hard, right? Do you make things more complicated than they need to be? Yeah. Don't do that. So this is just step 2. Compare the exponents. If the base is the same on both sides, you just compare the exponents and you say what it has to be. So just one more easy one like that, okay? Example 2. 2 to the x plus 1 equals 2 cubed. A little bit more complicated. You might have to think a little bit more. I still want you to be able to do this in your head, though, without writing anything down. What would the answer be? X would have to be 2, because 2 plus 1 is 3, and this side is 3. So you say to yourself, okay, the base is the same. I just compare the exponents. So the process would be this. You're not really dropping the 2's, you're just saying they're already equal on both sides, so I don't care about them because they're already equal. So then x is 3 minus 1, which is 2, so the answer is x is 2. Okay, now up here I say the procedure is to rewrite both equations so that we can do this. This is type 1, the ones that are easy, that we can just make them look the same. Okay, so let's get a little bit more complicated. Now these are all going to work out, so here the bases on either side don't match. One's a 3 and one's an 81, so you can't compare anything yet. But can you change the 81 to be 3 to some power? That's the question. So what are the powers of 3? Like 3 to the 0 is 1, 3 to the 1 is 3, 3 to the 2, 9, 3 cubed is 9 times 3, 27, 3 to the 4, 81, and you need to know them up that high. Okay, so that's sort of a memorizing thing. You need to know the powers. We don't use powers a whole lot, so sometimes you don't know them right off. But what you do know right off, I think, is square roots. Like if I said the square root of 9, you already have that memorized as what? 3. And what about the square root of 144? 12. You have some square roots memorized. But if I said this one, like 81 is 3 to what power, you maybe don't have that memorized. It's 3 to the 4. You need to. So I'm going to tell you how far up you need. For 3's, you need to go to 81. Meaning that on a test I could put a 27 and I expect that you can easily say that that's a power of 3 or 81. Okay, so you want to recognize the powers of 3 up to 81. So we would rewrite this. 81 is 3 to the 4, and so what's the answer? 4. You compare the exponents. We got the base the same, and now we compare the exponents. So what if we did powers of 2? So 2 to the x plus 1 equals 16. So let's write the powers of 2. So 2 to the 0, 2 to the 1, 2 squared, 2 cubed. You may even know that one right off. 2 times 2 times 2 is 8. What's the next one? 8 times 2, 16. 16 times 2, 32. 64. 128. That's how high I expect it, for 2's. So if you see a 128 in the question, you say that's a power of 2. Okay, so in this section, I want you to know up to there. 2's are more useful in general. Okay, so what's 16? 2 to the 4. So we would say, okay, 2 to the x plus 1 is equal to 2 to the 4. The bases are now the same, so we can just compare the exponents. So the answer is 3. So far, so good? They get harder. They always get harder, right? Because I'm going to add fractions, negatives, stuff like that. All right, so let's see. The next one. Okay, so this one's a little different. What base do you think we might want to make both sides equal? 25. Thank you, because that's the wrong answer. I always like the wrong answer. It is. Why? So I wanted you to think it was 25, and that's why I asked. So when you get something wrong, you never get it wrong again. I like you to get it wrong. In class where it's safe to get it wrong, on a test it's not so good. So why is it not 25? What is 25 squared? It's 625. So we can't write 125 as a power of 25 because the first power is bigger than the number we have there. But you might have to change both sides. So let's write down the powers of 5. 5 to the 0, 5 to the 1, 5 squared, 5 cubed. So this is 1, 5, 25. 25 times 5, think of quarters. 5 quarters is $1.25. That's as high as I expect you to know for 5. Okay. So what's 25 as the power of 5? 5 squared, or 5 to the 2. So this side is 5 to the 2. Now there's already an x there, but it would stay up as the exponent. Okay, we just multiply it. And on this side, 5 cubed. So now the bases are the same, so we can compare the exponents. And the answer is 3 over 2. Okay. Now we're adding a fraction. So with 4's, you can write them as base 2, or you could write them as base 4 if it works. But any power of 4 is 2 squared, so 2's or 4's work here. What are the powers of 4? 4 squared, 4 times 4? 16. 4 cubed, any idea? It's 64, and that's as high as you'd need to know. But again, you could just use powers of 2 for this and get the same answer. So you could say, well, 64 is a power of 2 and 4 is a power of 2. We'll do it both ways to show you. So say we wanted the base to be 4. So this side is a problem. When you're comparing bases, it can't be in a fraction, it has to be on top. So how do we move the 4 up to the top? 4 to the negative x, because there's an x power here, so this is 4 to the negative x. And 64 is 4 cubed. Now be careful, we want to multiply the exponent that's already there by the 3. So make sure you put it in a little bracket. The last one was similar to that, but it was just an x. So when I put the 2, it's just 2x. This one has more than one term, and we want the 3 to go with each of it. Now the bases are the same, so we can say minus x is equal to 3 onto 2x plus 1. And we can work this out. 6x plus 3. So x is minus 3 over 7. So what if we wanted it to be base 2 instead? Either way would work in this particular example. So if we wanted a base 2, I would still do that same first step, move them up so that they're both on the top. So this would be 4 to the negative x. And 64 as a base 2, which one was it? 2 to the power of 6 is 64. So on this side, 64 is 2 to the power 6, and we've got a 2x plus 1. So instead of 64, we put 2 to the power 6. This is 2 squared. 2 times minus x. So this is 2 to the minus 2x, and this is 2 to the 12x plus 6, if you multiply that out. And then the same thing, so minus 2x equals 12x plus 6. So x equals minus 6 over 14, which reduces by 2. Same answer. Okay. So with 4s, you can just ignore the powers of 4 altogether, really. But I do expect you to be able to recognize that 64 is the power of 4, 16 and 64. Just those ones, though. Okay. What other power do I want you to know is 10. And 10 is really easy. What are the powers of 10? 10, 10 times 10, 100, 100 times 10, 1,000, 10,000. Any power of 10 is fair game. Count the zeros. So let's say, for example, number 7 is square root of 10 is equal to 100 to the x plus 1. Now when I put a radical in there, people get confused, but what is the power? 10 to the what power on this side? A half. So you'd write that as 10 to the power half. And 100 is 10 squared. So on this side, what would we write? 10 squared times x plus 1. So this would be 10 to the 2 x plus 1. Multiply the exponents. And now we've got a base 10 on both sides. So we can say 1/2 is equal to 2 onto x plus 1. Multiply that out. Common denominator. That's like a 2 over 1. We multiply by 2. So here we've got minus 3 over 2 is equal to 2x. Now how do we solve that? Divide by 2 or cross multiply. So that 2 goes down here. So x is equal to minus 3 over 2 times 2, which is minus 3 over 4. And last one from this section. And don't be scared when it's E, because you have less thinking to do. You don't have to think of powers, because the E will just be there with the power. What do we need to do, though, before we compare the exponents on this side? Move it up, because they can't be on the bottom of a fraction. So this would be e to the minus 3 is e to the x minus 2. So minus 3 is x minus 2. So minus 1.